Hello, Physics 2211. Today we're going to discuss the motion of a spring pendulum. By spring pendulum, I mean a rope with elasticity, causing it to oscillate in both the x and y direction, while the top end of the spring is fixed, much like in extreme sports like cliff jumping. We'll discuss Newton's law and the energy principle, analyze a real-life example in Tracker, model it in GlowScript using the second law to predict motion, and then compare it to two models. We'll use this comparison to defend or reject the energy principle and perform an energy analysis using the simulation and discuss the x and y periods of oscillation. So what is our system? We have a mass suspended by a spring with one fixed end. When dropped from rest, it will swing like a pendulum and also oscillate up and down due to the spring force, giving the mass an elliptical motion. This is because as the mass swings, the spring force changes. This is because the spring force is proportional to the displacement or the compression and extension of the spring. To analyze the scenario, we'll use Newton's second law and the energy principle. The momentum principle will help us predict the next position of the mass by using the net force to calculate velocity. We can use this incrementally to calculate the net force, which will change because the spring force changes. The energy principle states that the total energy is the sum of the potential and kinetic energy, and that work is the change in total energy. If external work is done on a system, that also means the energy of the system will remain constant, and any increase in one type of energy will be coupled with a decrease in another. In our experiment, we tracked the position of the mass as it moved and used the output to compare our computational model. We also use the tracker model for initial conditions such as x initial, y initial, the initial length of the spring, the rest length, and the spring stiffness constant. The spring stiffness constant and the rest length were calculated using the equation for the period of a spring and a force analysis at rest. Using the experimentally obtained y period of the spring, k was found to be 0.683 using this equation and the period here. The rest length of the spring can be calculated using k, because at rest, the spring force is equal to gravity, meaning that F net is 0 and mg is equal to k times the displacement squared, which can then be used with the current length to find L0. After obtaining data, we moved on to the GlowScript model, where we used initial conditions of mass, position, velocity, delta t, the spring constant, L0, and initial spring displacement from Tracker. Next, we iteratively calculated the position and velocity of the hanging mass using the momentum principle as shown. Each time the position of the mass changed, so did the spring force and the acceleration, impacting the mass's momentum and resulting in an elliptical orbit. We also used GlowScript to graph the predicted changes in energy using gravitational potential energy, spring potential, and the kinetic energy, summing to the total energy. Here you can see that the x and y position predictions were fairly accurate, but may have been skewed by our compounding intervals of estimation, meaning we took a unit of time and estimated linearly over that portion. However, that might not be what happens in reality. There's also friction and air resistance not accounted for in our ideal system that does exist in our experimental model. Here you can see that the total energy of the system in the simulation remained constant, and that when kinetic energy was increasing, the mass was at the edges of its ellipse here and slowed down towards the tips. This is a graph of the change in energy, and you can see multiple components of the total energy which remain 0, including the change in kinetic and potential energies that add up to no change in total energy, so no work done. After all, does this support the energy principle? Yes. Because no outside work was done on the system, the total energy remained constant, or the change in energy was 0. So in other words, the system was closed and therefore no work was done. Now, what can we say about the x and y periods of oscillation? We could calculate them using the average of the first 4 full oscillations. In this, I found that the x period was 1.67 seconds and the y period was 1.52 seconds. They can be different because of the elliptical shape of the orbit and 2 different types of potential energy in the system, making it so that the gravitational potential energy doesn't directly increase when the kinetic energy decreases. Today, we learned how to analyze the motion and energy of a spring pendulum. Thanks for watching!